we have seen 8051 microcontroller. So the next microcontroller which we are going to take up is the PIC family, okay, the PIC microcontroller. So here we are going to discuss about why we need another microcontroller when we have 8051, and the families, PIC microcontroller families, and especially PIC 16F877 architecture is what we try to see. Instruction set of PIC is what I try to take up in the next class. So in today's class, what I do is I will introduce the PIC microcontroller. So I will introduce PIC microcontroller, and we try to see the architecture of PIC microcontroller in this particular class. All right. So now let us start with why we need a different microcontroller when we have 8051. So the term PIC stands for Peripheral Interface Controller. Peripheral Interface Controller, PIC. Okay. And we will try to see its architecture. And we are going from one family to the another family, Intel. So from Intel 8051 to the Microchip PIC microcontroller is what we are trying to take up now. So then when you are moving from one microcontroller to another microcontroller, how to choose a particular controller, what are your needs, and then how to choose is what very important. There are n number of varieties of microcontrollers available in the market. So how to choose, what are your requirements, and according to your requirements, how to choose microcontroller is what we are trying to see in this particular class. Now, why we need PIC architecture? So this is used in embedded processing. That means the embedded processing is pervasive. Means the electronic intelligence in every day we need in products like the philosophy which we choose for selecting any particular microcontroller would be this: have the product that fits the problem. Okay, and many systems can be automated using 8-bit microcontrollers, and much of the product line is 8-bit. What do you mean by this? So the microcontroller has the feature of CPU and non-volatile program memory and resettable non-volatile data memory, RAM for data storage, and direct support for various input-output operations. So all the products we can incorporate this PIC. Right? And the applications of the controllers, now we will try to see automotive airbag systems and remote control. So today's remote control and handheld tools, and you can find in applications like coffee pot, mixer, stoves, refrigerator, dishwasher, and dryer. And major home applications, home heating systems and cooling systems will be using microcontrollers. And cordless phones, cell phones, we have microcontroller applications. And coming to the security systems, n number of applications we use microcontrollers. Television, DVD player, recorder, we use microcontroller. Sound systems, so on. And if you try to see the applications, the engine control 32-bit microcontroller. For engine control you can use 32-bit. And for transmission control, you use 16-bit microcontroller automatic. And audio system uses 16-bit. And anti-lock braking system uses 16-bit. But up to 50 applications, you have 8-bit microcontrollers. If you try to use the usage of this in automotive sector. So 8-bit, up to 50 or 8-bit, but engine control is of 32-bit microcontroller and transmission control is of 16-bit microcontroller and audio systems, it will be of 16-bit microcontroller and anti-lock braking system will be 16-bit microcontroller. But up to 50 applications like airbags, electric mirrors, the mirrors, when you park your vehicle aside, then any other vehicle can hit the mirror if it is nearer, if it is moving. Then what you can do, you can close your mirror. So then you can use this electric mirrors, which automatically closes. Wiper control, electric mirrors, airbags, and fuel pumping, and speedometer, and security system of the car, climate control, and power windows. For all applications, you will be needing only 8-bit microcontroller. Okay? And this PIC microcontroller is proposed by Microchip. And now the popularity of Microchip, if you try to see, in 1990 ranking, then the ranking of microchips comes after. The first one is Motorola, Mitsubishi, National Semiconductors, Intel, Hitachi, Philips, okay, and then National Semiconductor, NEC, after NEC, National Semiconductor, Siemens, TI, Sharp, okay, Toshiba, and Zilog, and Sony, AMD, and Microchip. So this is what the place of Microchip in 1990. In 1993, then the Microchip position you can see. In 1996, then the Microchip position you can see here, how it is moving up. And in 2001, a survey says, after Motorola, it occupies the second place. And in 2002, it occupies first place, the Microchip. Then what is the reason, the usage of, now if you try to see the microcontrollers, 8-bit microcontroller, 4-bit and 16-bit, 32-bit microcontroller. From 1995 to 2000, the usage of these microcontrollers are increasing, and the market share, if you try to say, slowly the Microchip family is taking care over of the other families. So then what are the parameters you have to choose, or what are the specifications you have to choose to pick a particular microcontroller? So then the first thing is number of I/O pins, how many number of I/O devices it can accommodate. Then the amount of program and data memory it has on chip. Because if you are writing in a complex and the lengthier program, it should have enough memory. And speed, the clock speed. And then on-chip timer resources, how many timers are available, and what features the timers are, and interrupt control, how many interrupts it can accommodate, how robust it is, and error recovery. This is very important. When there occurs an error, automatically, if watchdog timer is available on chip, then it restarts. Okay, it restarts your system, so that your controller will be on safer side. And I/O expansion facility, whether you can expand the input output facility or not. Then every 8051 we have seen there are 32 I/O pins. 4 ports are there, port 0, port 1, port 2, and port 3. Then, but if I need further, well, can I extend it or not? Yes, we can extend it in 8051, but we need another IC 8255 need to be interfaced with 8051. But whether you can, no, instead of going for another IC, whether you can extend the feature of the IO ports or not is what now need to be seen. And coming to the PIC architecture is an Harvard architecture. Whereas the microprocessor which we have seen is of von Neumann architecture. Von Neumann architecture where you have CPU and here you have one memory. So okay, then memory or RAM or ROM. So you have only one address bus to identify the memory. So to identify the memory, okay? And you have one data bus to bring the instruction or data, opcode or data from the CPU. But whereas in PIC architecture, it is in a Harvard architecture. In Harvard architecture, what you are going to do is, what is the feature of this is you have an CPU, and let us say you want to work on a huge data. So you have a separate data memory, and the code which you are writing would be in a separate memory. So you have separate program memory, and here you have separate data memory. So then there are separate different buses for identifying the program or code. You have separate address bus, and for identifying the data, you have the separate address bus. And similarly, this, to bring the instructions on the CPU, you have separate bus, and to bring the CPU on the data bus, you have separate data lines. So here, this is the Harvard architecture where you have separate address bus for program memory, separate address bus for the data memory to locate the data. Okay, and separate data lines to bring the data into your CPU, and here to bring your instructions on the CPU, you have separate data lines. Then the advantage of this is that multiplexing concept which we used in 8051, in which the port 3, the port 0, it can be act like port 0 or address or carrying data. Three functions are done the same, right? So, but here you have separate address and data so that the speed of the microcontroller will be very fast. So now if you try to see the feature of the hardware architecture, all instructions are single instructions. This is important. Coming to the microprocessor and microcontroller, we can classify them as like CISC and RISC, reduced instruction set and complex instruction set. So here in RISC, all instructions are single cycle executed instructions, only when fetch for instruction, and the instruction fetch and execute are pipeline, so you can operate at near clock rate instructions per second. So you have two separate buses, one for instruction and one for data, so speed is more. And now if you try to see the complex instruction set with the reduced instruction set, the olden days if you try to see, the memory was very slow and very expensive. So, and the programming was done in assembly language. As the instruction could be retrieved up to 10 times faster from a local ROM than from main memory. So programmers try to put as many instructions as possible in a microcode. So in CISC you have the machine instructions and then microcode conversion and then micro instructions and then micro instruction execution. This is what used to happen. But in RISC, the relatively limited number of instructions, smaller number of type of computer instructions so that it can operate at higher speed. So now if you try to see the some of the low-end devices of this PIC, if you try to see, they are 12cc5x, 16c5x, and 16c505 kind of. And coming to the mid-range PIC architectures, they are built by upgrading low-end architectures with more number of peripherals, more number of registers, and data program memory. So some mid-range devices are 16cx, 7x, and 16f87x. So this is what is there in your syllabus. So here, C stands for means the ARM chip memory is of EEPROM. And 16F means it is flash. And RC stands for mask ROM. And these are available in the dual inline package. Dual inline package, and you have the PIC microcontrollers are available in DIP or PGA, pin grid array kind of thing. It is surface mount package. It is surface mount package. Okay, so this is PIC. So they are available either this or this form. So sometimes you try to find the PIC 16F87A. So this A stands for, this is suffix A. The meaning of this A indicates it is brown out reset. It indicates brown out reset. So what do you mean by this brown out reset? The brown out reset which causes reset of the PIC. Reset of the PIC when the power supply voltage drops below 4 volts. What is this A? PIC 16F877A. So PIC stands for what? The PIC which we are dealing the microcontroller. Peripheral interface controller. 16F is the family. So here F stands for what? F is flash ROM. The on-chip memory is a flash. And then this A is brown out reset. So what do you mean by brown out reset? Facility which causes the reset of the chip when the power supply drops below 4 volts. And the features of this, if you try to see, it has 35 instructions only. It has 35 instructions only. Okay. And integration of operational features. Power on reset, that's what we discussed. Power on reset and brown out production. So this is what A stands for, brown out production. So this ensures that the chip operates only when the supply voltage is within specification. Okay, within specifications of voltage levels. And the watchdog timer, which is very, very important. So there is an on-chip watchdog timer. So it resets this controller if the chip malfunctions or deviates from its normal operation at any time. So the watchdog timer, it resets the PIC if the chip malfunctions or deviates from its normal operation at any time. And powerful output pin control. It has powerful output pin control. So single instruction can select and drive a single output pin high or low in its 0.2 microsecond instruction execution time, a bit programmable, and then the pin can drive a load of up to 25 microamperes. And the speed of the pin, it executes instruction in 0.2 microsecond or 5 instructions can be executed per microsecond. And the I/O port expansion, so with the help of built-in serial peripheral interface, so with the help of to expand the number of port pins available for 8051, you can expand it by using connecting 8255. But here you have inbuilt serial peripheral interface SPI, so the number of I/O ports can be expanded. Right. So then we'll try to see how it can be done after we see the port pins of PIC microcontroller. Okay. And the interrupt control, it has up to 12 independent, and the capability of microcontroller depends upon how many number of interrupts it can handle. Means it can service the devices, the number of devices it can service. So up to 12 independent interrupt sources can control. The CPU will interrupt sources, it can manage. So that is also one more very important feature of the PIC microcontroller. And coming to the timer, you have 3 timers. Timer 0, timer 1, and timer 2. So the timer 0 is an 8-bit timer counter with 8-bit prescaler. So now you can compare the features of 8051 with PIC microcontroller. So the timer 0 is an 8-bit timer counter with 8-bit prescaler. Timer 1, it is a 16-bit timer. It is a 16-bit timer with prescaler can be incremented during the sleep via external crystal clock. This is what the additional feature. So the timer 1 is a 16-bit timer counter. It has a prescaler and can be incremented during sleep via external crystal clock. And timer 2 is an 8-bit timer counter with 8-bit period register, prescaler and post-scaler. And the pins of this one, the additional feature is PWM. PWM, pulse width control, can be generated by using this PIC microcontroller, which is very, very important to generate the pulses with different, to generate the frequency with different pulses. And it has synchronous serial port SSP with SBI TM. And universal synchronous asynchronous receiver transmitter USART are known. And parallel slave port, it has a parallel slave port are 8 bits. Just now I have shown you, this is what, it has an on-chip serial peripheral interface by which you can extend the I/O ports. You can expand the I/O ports. With the help of parallel slave port, which is of 8-bit with external RD, read, write, and CS control. The brownout detection circuit for brownout reset, and the PIC, that is what we just now discussed, the A. And the PIC 16C-XS microcontroller family has enhanced core features, 8-level deep stack, and multiple internal and external interrupt sources. And now if you try to see the pins RC2/CCP1, it is capture one input or compare output or PWM output. And RC3 is synchronous serial clock input output that is SBI and I2C. Okay, and coming to the ports, so port A is a bidirectional IO port, and RA0 can also be analog input. So one more important feature of microcontroller, PIC microcontroller, is it has onboard A to D converter. So coming to the 8051, what we did to interface sensors to the microcontroller 8051, we did this with the help of A to D converter interface. But PIC microcontroller has onboard A to D converter. So then RA0 can also be analog input 0, RA1 can also be analog input 1, RA2 it can be analog input 2. So then RA0, RA1 and RA2 they can be analog inputs, or otherwise that can function like AN0, right? AN1 and then AN2, other functions also. So multi-functions. Microcontroller, this is what the difference. Microcontroller, each pin will function differently, but whereas in microprocessor, this facility is not there. Then RC0 can also be, the timer 1, the RC0, right? And RC1 can also be the timer 1 oscillator input. RC0, RC2 and RC3. And port B is a bidirectional IO port. So port B is a bidirectional IO port. And RB0 can also be the external interrupt pin. And RB4 can be interrupt on change pin. And RB5 is interrupt on change pin. So RC4 is an SPI data in, by which we can extend the ports, and RC5 can also be the SPI data out. And RC6 can also be the USART, asynchronous transmitter or synchronous clock. So this is the pin diagram of the PIC family 16667XX. And now, if you see the architecture of PIC microcontroller, then if you try to see the architecture, as I told you, what you can see here on the architecture of a microcontroller. So it is Harvard architecture. So Harvard architecture means you should have separate address bus and data bus. So separate address bus and separate data bus for program memory and data memory, right? So then you have an ALU with an accumulator, and here you have onboard ports, and here you have onboard timers, and you have onboard interrupt facility. Okay, interrupt facility, and you have on-chip watchdog timer. Right. So the moment you see the architecture, these are the things you can find on the architecture is. So now, this is what your ALU, which is of 8-bit ALU. So that's why we are calling it as 8-bit microcontroller. Just now I have shown you in automotive industry, about 50 applications are 8-bit microcontrollers. Okay, 8-bit microcontrollers. That is 8-bit, based on, we can say the ALU of it is 8-bit. ALU of this is 8-bit. So here you have 5 ports: port A, port B, port C, port D, and port E. 8 ports. So ALU and status register nearby ALU, and you have general purpose registers. Okay, general purpose registers. So that is RAM files, and then which we can use it as registers also. So here only 16 bytes is what you can use in RAM, 256. But here more number of registers are available. So here if you try to see, this is of 8-bit. So the data bus, for EEPROM by program counter. Now if you try to see, okay, this is what the program counter. This is what EEPROM, and 8-level stack, 8-level stack feature. This is program memory, right? So this is program memory with it has separate address and data buses. Right? So then here you have an instruction decoder, right? Instruction decoder. Then you have on-chip timer, timer 0, timer 1, and timer 2, right? And ports, right? Ports and USART. And as we said, this PIC microcontroller has on-chip A to D converter, right? On-chip A to D converter and parallel slave port and the instruction decoders and also on-chip RAM and have ROM and timers and serial USART, right? And you have ports. Right, you have ports and so on. Okay, so this is what the architecture, but architecture is a little bit different. The ALU and you have the W register here within a box. So we'll try to see the operation of this in detail. So these are the features of 16C7XX. So this is brown. This is the highest bits are from status registers, and now you can check it out. So these are the additional. Okay, these are the additional features with 16 PIC. So now if you try to see 16.6X family, then it has only port A and port B, but whereas here in 16.6X family you have 3 more ports added up. And coming to the pin package, already we have seen that is available in DIB or surface mount package. PIC microcontroller 16F877. And the same thing now in detail you try to see 16F877 architecture. You have the CPU block diagram level if you try to see. You have the CPU, you have the program memory, you have 13 bits of program address. 13 bits. So 2 power 13, which is of 2 power 3, 2 power 10. So 2 power 3 is how much? 8 kilobytes. So 8 kilobytes of program memory. Right, you have the instruction, instructions bringing bits are 14 at a time. And the data memory, okay, the data memory, that is a special registers, okay, which is of 8 bits register address bus and 8 bits data bus. And you have general purpose registers n number. So this is RAM, and then this is what your EEPROM, where your code runs, okay, and then where your data runs. And in detail, if you try to see this 16, so here you have 14-bit data bus to carry data or instructions. Instruction bus, or you can say from program memory. So this is what it is identified, 14 bits. This is flash program memory. That is what the difference is. Here it is EEPROM. This is PIC 16C66. This C stands for, this is of EEPROM, but this microcontroller 16F877 is of, are having on-board or on-chip flash memory, right? So then this is a 14. That is what the architectural difference. Here you can go ahead. So this is a 14 bits, right? And this is of 8 bits. So this is what your data memory, RAM, RAM, right? So then this is what the program counter, which point out the next instruction to be fetched by the microcontroller. So this is what the program counter, and this is what your data memory. So the data memory bus width is 8 bits, and program memory address bus is 13 bits. So by which you can say the onboard flash RAM, how much it is available. And then we have the instruction register, and then it will, the instruction decoder can decode these instructions, and then the ALU can execute this. So the ALU can execute this and can take a decision. Okay. So then here you have a LU and flash program memory. This is how it is different. The timer 0, timer 1 and timer 2, and on-board 10-bit A to D converter. On-board 10-bit. So when it is of 10-bit, so then 1 by 1024, right? 10-bit means that is the minimum voltage it can recognize or detect. Okay, right? So here you have port A, port B, port C, port D, and port E. And port 0 can, it can act like input-output port, or the analog to digital converter inputs can be given to this port A, RA0, RA1, RA2, RA3, and RA4. So there are, right, so there are RA0, RA1, and RA2. So 3-channel A to D converter. Okay, 3-channel analog to digital converters, right? And which is of 10-bit on chip, right? And so here you have onboard watchdog timer, and you have onboard brownout reset. So what is this brownout reset? Is what we said. If the power supply to the pin of this chip, if it is goes below 4 volts, so then automatically it resets. Automatically it resets the microcontroller. Okay. So this is direct address register, and then this is what your data RAM, and then this is what your program RAM, program memory. So then this is what your data RAM and the ports available. So the difference is you have 8051 architecture and this architecture. You have flash program memory here. You have onboard 10-bit A to D converter. So here you have parallel slave port. So parallel slave port. So you can extend the ports by using this. You can extend the port by using this parallel slave port. Right? So then ALU is up with the W register. Okay. And then this is data EEPROM and synchronous serial port. So onboard USART. So onboard USART you have. So these are the features of 16F77 microcontrollers. So the program memory, you have 13-bit program counter. So as I said, you can go up to, so addressable up to 8K, and 8K 14-bit, right? And flash memory reset vector is 0000 and interrupt vector is 0004. So this is what your program memory is, on chip program memory. Page 0, page 1, page 2 and page 3, and the reset vector here is from 0004, and here you have 8 levels of stack. So stack level 1, so stack level 2, and so on up to stack level 8, right? So this is what on board program memory. And coming to the data memory, it is partitioned into 4 banks, and each bank is of 128 bytes. 8051 divided into 4 banks, each bank is of 8 registers, 8 bytes. But here each bank is 128 bytes. So 128 into 4. So which is of 512 bytes. So you can understand the architectural differences of 8051 and PIC microcontroller. So then the upper locations are general purpose RAM, and lower locations are special function registers. Whereas in 8051 also, the lower section is of general purpose register, and then the upper section is of SFR. So now if you try to compare PIC microcontroller with 8051, so PIC microcontroller you have 128 bytes memory, 128 bytes memory. So the lower section is register file 0, 1, 2 and also lower size is 4 banks. So 432 bytes are for this general purpose register. And 80 and all, so they are the special function registers like tmod, tcon, sbuff, scon, okay, and bit addressable memory and all. That is of 8051. But here you see it is reverse. So the upper location is general purpose registers, the lower location are SFR, special function register. So the bank selection can be done by using this status registers. RB1 is up to 6, RB0 up to 5. So if they are 00 bank 0 and 01 bank 1 and 10 bank 2 and 11 bank 3, and each bank is of 128 bytes. Each bank is of 128 bytes. To try to understand now the data memory of this PIC microcontrollers. And coming to the ports, we have seen 8051 ports thoroughly. The port pins now, if you see, you have data latch and S latch, and you have bidirectional data buffers. And then this is what your MOSFETs. TTL input buffer. So while data is in, so while it is active input port, the data can be connected to the input port this way. And when it is an output port, it simply uses a buffer. Latch. For input port you require buffer, and for output port you require a latch. Okay, so now you can try to see. So this pin is becoming 0 or 1, so writing 1 or 0, easily you can understand this particular logic. Alright, so now these are the interrupts features. The port pins, now here, the important point is how to make the PIC controller pins as input ports and how to make it as an output port in programming point is what I'll try to discuss. Now I'm trying to discuss only the features and then how they are different from 8051 microcontrollers. And these are the interrupts. So this is very important. And these many interrupts can be serviced. 12 interrupts can be serviced by PIC microcontroller. That's why it is popular. And you have commercial code dumpers are available. So you can program your PIC microcontroller by using this. You can buy it. Now it is available on Amazon also. Amazon, Flipkart. So this is simply you can write. You can place your microcontroller here, and then you can download your code, the assembly language code from your key or some other compiler onto your EEPROM. Right? And coming to the bootloader options, so it is also known as bootstrapping or bootloader. So it's a program that resides in the computer's EEPROM, ROM or other non-volatile memory that automatically executed by the processor when the computer is turned on. Bootstrap loader or bootloader. It is a program. So what is bootloader? So for dumping your program, if it is 16C onto the microcontroller, you can use bootloader. What is this bootloader? It is a program that resides in your computer, okay, or other than that automatically executes by the processor when the computer is turned on. Alright. So now if you try to see, so these are the features of 16F77 microcontroller and its architectures. Okay. But the architecture here is Harvard architecture, as we said. Okay, Harvard architecture. So now the features, if you can summarize, the CPU is manufactured in RISC, reduced instruction set computer, and the RISC stands for reduced instruction set computer. It has 35 simple instructions, only 35 instructions, and execution time is 4 clock cycles, which is of 200 nanoseconds. The jump and branch instructions, they can be executed in 2 clock cycles. And operating frequency of the 8051 is 11 megahertz. And it executes 5 million instructions per second. See the speed. 5 million of instructions per second. So it's a CPU. So it's a Harvard architecture. Now you can see how it differs. So RAM is of 328 by 8, 36 by 8, EEPROM 8K of 8 kilo, each of 14 bits, not byte. 8 kilo locations of, each location is of 14 bits. The memory, the RAM and ROM. So that is how it is different. So onboard timers you have, onboard EEPROMs you have, onboard watchdog timer you have. Okay, so the memory is that is of general purpose and special function registers for timers and other things. This is what the conclusion is. It is used for storing temporary data and results created. So the functions are predetermined and the manufacturing process. So their bits are connected to some on-chip modules like A to D converters, serial communication modules, and any change of their content will directly affect the operation. So coming to the memory, RAM, you have bank 0, bank 1, bank 2, bank 3. Each is of 128 bytes. Each is of 128. So the RAM 8051 is of only 128 bytes in total, but it has how much? 328. EEPROM is of 8K and 14 bits, but it is bytes. That is the difference. Okay. And now special function registers you can see now, like for controlling. Now here if you try to see SBUF, the moment you see this is related to the serial communication. And coming to the timers. So the lower section are SFRs and higher sections are registers, just reverse of Intel. So bank 0, bank 1, bank 2 and bank 3. Each is of 128 bytes. So 128 into 4. And coming to the stack, you have 8 levels of stack available. So now the CPU registers, so all SFR in PIC are 8-bit size. This is what important. So this ALU works with working register and nearby status register, and FSR is file select register. Okay, and all SFRs are so program counter, so 8 level stack. So these are the features, and all special function registers of PIC microcontrollers are 8-bit. And coming to the working register W, it is a temporary holding register called accumulator. So in 8051 we call it as an accumulator. Accumulation back, when the data is written back after the execution. And W content moved to some other register and then it can be accessed, used by many instructions as source of an operand or destinations for the results or execution of 8-bit regarding. So this is what your status register. So carry bit, so digital carry, 0 bit. So these are arithmetic or logical operations. So this is status registers. So which we call it as flag register. So not PD, not TO. So ready only after reset it will be get value. So T0 is timer out. Watches if the watchdog timer is out is occur. 1 means power up and 0 means sleep instruction. And PD is power down. Okay. And sleep instruction is, watches it if the sleep instruction is executed. 1 means power up, 0 means sleep instruction. And register bank select can be done by using these registers in direct way. Bank 0, bank 1 and bank 2, bank 3 can be done by using this. So register bank select, register IRP. These two are register bank select direct addressing. 0001 1011 means bank 0, bank 1, bank 2, bank 3. So selection, RP1. This is register bank select in direct addressing way, and the earlier one is register bank select, indirect addressing. If it is 0, then bank 0, bank 1 selected. If it is 1, bank 2, bank 3 selected. So this is register direct addressing. So FSR is a file select register and the special purpose register it is. So it is indirect addressing mode and 8-bit register file address pointer. Any address is first written into FSR, access entire register file. And INDF is special purpose register. It is not a physical register. It is addressing addresses register in FSR, all addresses. So register file 05, register file 068. So program counter is of 13-bit. So it is readable 0 to 7 and 8 to 12 is not readable. It is of 13-bit. So by which only we are going to access 18 kilo. 14 bits it has, each one. 14 bits, yes. So it is 30-bit wide, PCL 8-bit wide is readable, PC5 is not readable, but are indirectly writable through PC latch register. So this is program counter. So it is clear edge. So for clearing you can use this. Okay. So we have seen now this is what the okay. So the registers and architectures of PIC microcontroller. So in the next class we will be trying to see the additional features. Okay, additional features of the microcontroller. So today's class we have seen, like when you try to see one microcontroller family to the another microcontroller family, what features generally you select, right? So that is what we have seen in this today's class, right? And we have seen the architecture of the microcontroller.